supports where the continuity is needed. Okay, so very simple system. So even this kind of bridges are very, very common because they can make this kind of bridge in less than 1 week. So that's how long it takes to cast the concrete. Maybe the piers and the pile caps, those will take another 2 weeks. So in a matter of 4 weeks, you can complete this bridge and there will be traffic on top of it. So that's one thing, it really bothers me. I feel very bad when I see some of the bridges being built here in India. You come for one vacation, you see that's they started. Come back for the next second vacation, is still what people are working on it. So you are losing so much money and time and efforts because the cost also goes up. If the project is instead of 6 months, it's 2 years, then the price cost of the materials, everything goes up. In a matter of 2 years, the cost will be double or even triple, right? Is that what your experience is? But I feel sad. I said, what's happening here? Why are they taking so long? This bridge, in 4 weeks, it will be done. If they don't do it in 4 weeks, the contractor will get very heavy penalties, and they don't want that. And this project, maybe this entire bridge from here to here is probably about 120 divided by 3, about 40 meters or something like that, right? So for 40 meter bridge, the width will be maybe another 20 feet or 20 meter or 15, 18, 20 meters. And this may cost about less than $150,000, okay? So that's, you can get a feel for numbers that way. So it's very inexpensive bridge. But because of the continuity over the supports, you have lots and lots of cracks, hundreds of cracks and very wide cracks, because they're always optimizing the thickness. And if you optimize the thickness, you get a lot of cracking because you are making it more flexible. And then there is another problem. Everywhere these bridges are like in very cold areas. So anytime you have a crack, water penetrates the cracks, goes into the cracks, and then there is freezing. And when water freezes, it expands. That means it takes up more space, right? So the cracks are opening up. Every time there is freezing and thawing, it's actually becoming wider and wider. And then the dirt goes into that cracks, it will permanently keep it open. That's the problem. So once again, Shrikant did all of this work. We go to sites, we do the actual inspections, and we look at the crack profiles, crack widths, everything. And then if you see this one here, this is the coins are like a quarters. Like in India, we have coins. They have certain thickness, right? So easiest way to show to people is that's a 2-quarter crack. So 1 quarter is 1 coin, 2 quarter is 2 coins, kept side by side, and you insert it, it's still very wide. So that's a very wide crack. So if you see ACI 224.R, you will see the maximum width for, at least the recommended maximum width for this kind of cracks is 0.007 inch. And what is 0.007 inch in terms of millimeter? It's probably times 2.5, about 0.018 millimeter, 0.18 millimeter, I think, less than a millimeter. So that's very, very restrictive. I don't know if you can imagine that, but it's very, very restrictive. So, but in reality, on real bridge decks, we can get as much cracking as much as 0.1 inch. It's a lot of thickness. Okay, so that's a big problem. So our main goal was to somehow reduce the amount of cracking in our bridge decks, at least in the future ones. So remember, I think I mentioned it last time on Monday or Tuesday. I mentioned this. So each time you see such cracks, they have to, that's a requirement, they have to go and seal them. So each time you seal it, it will cost like $15,000, $15,000. So if they seal it 3 times, that's like close to $50,000, right? So what's the cost of the bridge? It's about $150,000. So you are spending more than a quarter of the bridge cost to seal that. So that's a big maintenance cost. So relatively speaking, it's a very, very big maintenance cost. So use of ECB, I think I'm not using the right version. I think we had a later version. But anyway, I'll quickly go through this. ECB is epoxy-coated bars. There is a lot of problems with epoxy-coated bars. What you see here is when we had a bridge that was in service for about 35 years. 1988, no, it's about 35 years in service. And they were tearing it down. They were removing the bridge to make a newer deck. So when we were tearing it down, they said, oh, we saw all these kind of epoxy-coated bar conditions. So we said, okay, why not we document this? So you can see how brittle these coatings become. They're very brittle. So it just peels off. Just you can, with your bare hand, you can just peel it off. So we think epoxy-coated bars are giving us protection, but it's really not giving the protection that we expect. So if somebody is trying to, convince you that epoxy-coated bars are very good, they can be good, but we have a lot of issues with epoxy-coated bars. And this is really, you can just break it, like it's very, very brittle material. So in the process, Prince Bar's work, this one. This is Prince Bar's work. This particular one is Prince Bar. So for one part of the project, long time back, I've been working on this for like more than 7 years. So the first part of the work, Dr. Das knows Prince Bar very well because they were working in the same lab in Michigan, in the United States. So, so what we did was we looked at a lot of bridges, we did inspections, and we found that the actual crack widths are very, very wide, as much as 1/8 of an inch, like 0.12 inches is a lot, about 4 millimeters, 3-4 millimeters. And as per ACI, it's allowed. What is allowed is very, very small quantity. So this graphic, without worrying about the numbers, you can see how much difference there is between what is specified in ACI and what we were observing in actual field. So with that understanding, we said, what is the effect of cracking? That's the first thing we started to look at. So what's the effect of chloride penetration into the cracks? So we did a lot of accelerated tests and very simple pull-out tests. This is not even a standard these days. They removed the standard. ASTM no longer considers this pull-out test with blocks of concrete as standard. That's gone. ASTM standard is gone. But we still wanted to do these tests. In these tests, you will see there is black bar, epoxy-coated bars, MMFX, and hot-dipped galvanized bars, then stainless steel bars. Some of them are here, sitting here, and then CGR, which is a continuous galvanized reinforcing bar. Okay, so all these are different corrosion-resistant bars, and we looked at the difference between the performance of all these corrosion-resistant bars. And we did accelerated corrosion tests. We had many cells, and we used to shock the reinforcement with very high voltage. So that's not necessarily a good thing, but we don't have time to do natural corrosion. So because we are comparing numbers, we thought that's okay. But many of the corrosion engineers who do the correct way, they don't like this kind of test. But unfortunately, we have to do things in a very accelerated manner, so we just did this kind of test. And we had lots of good things to show. And then we found one of the things we did was we used fiber in our concrete. to reduce the crack widths and to improve the corrosion performance. And in both counts, we were very successful. So the addition of normal polypropylene fiber, of course, I decided on very high volume or high fiber dosage. So like 10 pounds per cubic yard. I don't know how much it will work out to be in terms of kilogram per meter cube. Probably it's about 4 kilograms per meter cube or something like that. 0.7, yeah, something like that. I'm not I don't remember the conversion, but 4 or 5 kilograms per meter cube. So we used very high fiber dosage, and then in every single direction we looked at in terms of performance, it was very, very good. And once again, Jagdish, you have to say that how much I appreciate Srikant's help in this. He did all this work by himself, one person. So we also did sustained load effects on corrosion performance of all these bars. So we made small slab specimens. We have the reaction frame here, and then we apply load and keep it constant, and then do the accelerated corrosion tests. Okay, I think a couple of you we talked about this. I said I will show you the setup. This is the setup. Okay, if you want to discuss this more, we can talk about it later. So this is the setup we used. We used all kinds of corrosion resistant bars, and then we had comparative comparison of performance. Okay, and of course fiber reinforced concrete, you are all familiar with that. We used very high volume, high dosage, and then with fiber we again did the same experiments, corrosion, accelerated corrosion tests, and there were like many stations. Again, once again, one student was handling all of this. Okay, of course he had his own way to extract the data and collect the data, but it's a lot of hard work. And then we found that black bars or the epoxy coated bars are not really, helping as much as they are supposed to. But if you add fiber, that makes really big difference. Fiber is relatively cheap in the sense, at least we'll talk about it later towards the end of the presentation. So we also looked at deflections. With fiber, your deflections can be reduced significantly, and the corroded beams, the difference between corroded beams and uncorroded beams, the difference is also significant. So instead of going into all the details, I'm just giving you only the most important findings from this study. Now the main objective of this study was to study the cracking behavior. That's the most important to us. That was the objective of this project. So in that we used prism tests. Prism tests, we had again applied load in a horizontal frame, and then we looked at the crack widths for different types of corrosion resistant bars, with and without fiber, So we have lots and lots of test data. Of course, Srikant also did a lot of theoretical work, and he tried to correlate theoretical predictions with the actual test results. So once again, without going into the details, fiber did help a lot in terms of crack width and crack propagation. So these are some of the failed prisms. Then we also did some fluxural tests, beam tests. So in the beam test, we actually simulated the 3-span bridge by testing this part only. So that's a 3-span continuous bridge. So you have support here, there is inflection point here. Inflection point is point of zero moment. So inflection, zero moment here, zero moment here. We isolate this element, and we actually tested everything to represent this small element. Even though it's a very long bridge, very very long bridge. We were able to test only this small length, and then we were able to get the results that correlate with full-scale tests. So initially we were not sure, so Shrikant did some very long beam tests, 15 feet to start with, and then he did 30 feet tests also. He correlated between the scale tests and full-scale tests, and then we found some correlation, and then we also got our crack width predictions from the actual theoretical work, and then we did very long beam tests. This is probably about 24, 30 feet. 30 feet is like 30 feet is like how much? It's a lot. Let me. About 10 meters. Slightly less than 10 meters, but about 10 meters. Okay. Yeah, yeah, almost. Yeah, a little bit less, but it's very, very big test actually. And then we scaled it down because we cannot do full scale, many full scale tests. So we understood the beam behavior under full scale test, and then we correlated with small tests, and then we moved on to 4 meter tests, very small by our standards, and we tested many of these, many of these, maybe 30 or something like that. Okay, once again, the same trend was observed. So like with fibers, you reduce the crack width, you reduce the deflections, you reduce the corrosion effects, so on and so forth. So fiber, in our view, worked very, very well to reduce the crack widths and to reduce deflections. And then fatigue, we did some fatigue tests, and we ran up 1 million cycles. 2 million cycles actually, 2 million cycles. And then once again, if you add fiber, your crack widths can be significantly reduced by fibers, fatigue crack widths. So when the sponsor, the one who gave us funding, he looked at all the results, they were very happy. They said, let's implement this in a bridge. So that's a bridge we used in one of our nearby counties, nearby areas. We did a 3-span bridge with actual fiber with 10 pounds per cubic yard dosage. Very, this is what they do. We were not able to use the pump, so we used conveyor. So you dump the concrete here, it is conveyed on the conveyor belt, and it worked very, very well. Very good surface. Everyone was very happy. So, and then the finishing was perfect. If the constructability is not acceptable, they will never let us implement any changes. Unfortunately, they will not agree to that. But in this case, every single thing was perfectly achieved. So finally, we got very good surface. They are very happy with that. Like again, you can see there are about 10 or 12 people who are actually making everything. There is very few people. You won't see many people on the construction site. And then we looked at the, this is a little bit, I think I'm missing 1 or 2 slides. But anyway, the gist is, in summary, we found that fibers have really helped in controlling crack widths. So ACI 222 limit of 0.007 inch is not achievable with the current specifications. We said either we should change the specifications, like the bridge design drawings, they are asking us to do something which is impossible, or they are asking the contractor to do something that's impossible. So we should either change the specifications or use some materials like fiber to actually achieve tighter crack widths. Okay, so with that, I will finish this presentation. Any questions? Questions?
Not related to this topic.
Yeah.
About the type ACI code or
222, yeah.
the crack widths for various cases, like chemical insulation,
Yeah.
water.
Yeah.
So whether they have given limits as 0.007
Yeah, that's a good point. I agree. Yeah,
It's not related to this topic, but I think how the codes have been devised.
I know. But see, they are not perfect, but we don't have anything else. Until you can have a better specification, we have to use what is currently available. That's the whole point of research. By doing research, you can suggest changes to these specifications. Anything else? Any other question? Okay, so I will show you one more presentation which is not necessarily FRP related, FRP bars, but it is related. So let me show you this. So I have a Norwegian company that sponsors my research, Reforce Tech, and I personally did a lot of work on basalt fiber. So to the extent that I have developed a design guideline just for basalt fiber reinforced materials. So this is one part of that whole thing. It's not exactly even, it's a small part of the whole project, but it will be interesting to see what it is. Okay, so we'll go over a couple of things like applications and characteristics and so on and so forth. So these are what's known as minibar, and I have a few samples here. There are so many generations of minibars. We change the design based on the performance. So we used to continuously go back and forth. So they change the product, we do the testing, and then we suggest some changes. They go back, change the product, and then send it back to us. So we used to go back and forth and make it work. Finally, what counts is it should work. Because industries, they are willing to spend a lot of money, but they want working results, not just theoretical papers. So this minibar product is nothing but it's a FRP bar at a very small scale, put it that way. And it will be mixed just like in fiber reinforced concrete, just like your polypropylene fiber. You mix this in the concrete mix and then make the concrete. If it breaks, when you break it, it looks like this. Very nice product, very, very good product. So the residual strength for this kind of material is very, very, very high compared to say polypropylene fiber or other non-metallic fibers. Metallic fibers are very good. They give you very good residual strength, but non-metallic fibers you cannot even mix in large quantities. That's the difficulty with non-metallic fibers. Okay, so then we have a few. We'll just move on. We'll not go through every single slide. So we tried dosages as much as 2.5–3% dosages, very, very high dosages. And if you are familiar with polypropylene fiber, if you are using 0.5%, you are very lucky. But with this minibar, we were able to use as much as 2.5–3% of fiber, which is very helpful. So we were able to do the ARS test. You probably are familiar with the average residual strength test. And then we were able to get 10, even 17 MPa residual strength. I don't know if you have a feel for numbers, but that's a very, very high residual strength. Average residual strength. It's a standard test, ASTM 1399. Cracking. Yes. Well, okay. The residual strength is what you do is you first crack the specimen and then let go of the. No, let go means don't load, release the load, and then you load it again after cracking. So after cracking, if you have no fiber, the concrete beams, what will happen to the concrete beam? There will be two pieces. Whereas with fiber, even after cracking, they won't become two pieces. You can still apply load and it will still carry load. So that's known as residual strength. So after cracking, whatever is the strength that remains after cracking is known as residual strength. And then 10-15 MPa residual strength is very, very high. It's not, it's spectacular residual strength. And you can see all these load deflection curves, very nice. What it means is for a very large deflection,